You ever feel that little zap of static electricity when you touch a doorknob? Or, when you rub a balloon on your head and it just sticks to the wall? That's not just some random quirk. It's actually a fundamental force of the universe at play. And today, we're going to pull back the curtain on this invisible push and pull and really get to know the law that runs the whole show. So here's our game plan. We'll start with that mystery of static electricity we all know. Then we'll decode the force behind it, break down the formula, see how it actually powers our world, and finally, take a look at the few places where the law kind of bends. All right, let's jump right in. Time to tackle this invisible push and pull and finally understand the everyday mystery of these static forces. I mean, we've all been there, right? You shuffle your feet across the carpet, you reach for the light switch, and zap, you get that little shock. Or the balloon trick, it feels like magic. But it's not magic, it's pure physics. So what is this invisible force that can push things apart and pull them together without even touching them? Well, the answer, it all comes down to something just as fundamental as mass or gravity. It's called electric charge. Pretty much everything in the universe has it, and it's the source of this whole invisible dance. This is the key. And here's the one simple golden rule you need to know. If two charges are the same, both positive or both negative, they can't stand each other. They push apart, they repel. But if they're different, one's positive, one's negative, they pull towards each other, they attract. Opposites attract. It's the basic grammar of the entire electrical world. Okay, so we know the basic rule. Opposites attract, likes repel. Now, let's actually decode the force itself. It's time to open up the official rulebook that tells us exactly how these charges are going to behave. And that rulebook has a name, Coulomb's law. It is a beautifully simple law that lets us calculate, with incredible precision, that exact push or pull between two little charged particles that are just sitting there. This law is the secret behind it all. And here it is. Now, I know what you might be thinking, whoa, a formula. But trust me, stick with me here. It's so much simpler than it looks. Think of it like a recipe for electric force. F is the force we're looking for, the Q's are our two charges, R is how far apart they are, and K is just a special number to make the math work out right. So now let's really put this law into action. We're going to crack this code open piece by piece and see how each part totally changes the outcome. The real magic of this law is how simple its ingredients are. First, you have F, that's the force, the final strength of the push or pull. Then you've got Q1 and Q2, which is just the amount of charge on each particle. You can think of it like their electrical size. Then there's R, the distance between them. And finally K, which is just a constant number we plug in to make sure the units all line up. That's it. And the relationship between these parts is what's really important. It's pretty intuitive. The bigger the charges, the stronger the force. Makes sense. But here's the real game changer. Distance. The force gets weaker as things get farther apart. But if you double the distance, the force doesn't just get cut in half. It becomes 4 times weaker. It drops off like a rock. That's called an inverse square law, and it's a huge deal in physics. And check this out. This is where things get kind of mind-blowing. If that formula looked a little familiar, well, you were onto something. Look at it right next to Newton's law of gravitation. The structure is almost identical. One describes the force between charges, the other describes the force between masses, but both of them have that same inverse square relationship with distance. That is not a coincidence. It's a clue that the universe has this deep, beautiful underlying structure. It's a cosmic parallel. So we've gone through the theory, which is cool and all, but let's get practical. How does this stuff actually show up in the real world? Let's see Coulomb's law at work. First things first, we've got to get a handle on the unit we're using. We measure charge in something called coulombs. But what even is 1 coulomb? Is that a lot? A little? Let's find out. Okay, get ready for this. Because 1 coulomb is absolutely massive. It is the charge of about 6.24 times quintillion electrons. That's a 6 with 18 zeros after it. It's a staggering number. A huge lightning bolt might have a couple dozen coulombs, but that static shock from a doorknob, oh, that's a teeny tiny fraction of just 1. And once you know how to control these forces, you can build some incredible technology. That photocopier at your office, it uses static charges to get toner to stick to the paper. Air purifiers zap dust particles with a charge so they stick to a metal plate. Even the paint on your car was likely applied using these forces to get a perfectly even coat. It is literally everywhere.
right down to the forces holding the atoms in your body together. Now, like any great law in science, it's really important to know where it works and where it doesn't. So for our last section, let's explore the limits. Let's see when the law bends and when we need to reach for a different tool. So here's the deal. Coulomb's law is perfect for charges that are sitting still. That's why we call it electrostatics. The second those charges start moving, you get magnetism, and that's a whole other story. The law also assumes you're in a vacuum. Put those charges in water or plastic, and the force actually gets weaker. And finally, the law is great at telling you how strong the force is, but it doesn't really explain how that force travels through empty space. For that, you need something called an electric field. But hey, that's a story for another day.
You know, this quote just sums it all up perfectly. It's not the whole story, not by a long shot, but it's the bedrock. It's the absolute foundation that everything else is built on, from the tiny circuits in your phone to the giant radio waves that connect our world. So when you think about it, we've uncovered this simple, elegant rule that governs a fundamental force we feel every single day. It just makes you wonder, right? What other profound, invisible laws are out there, hiding in plain sight, just waiting for us to figure them out? The universe is just full of these hidden codes, and we've really only just started to read the first page.